This video lecture is meant to cover the information found in Unit 9.1 on rate laws, but this information is not found in the Rosengarten text or in the Rosengarten videos. We're going to be learning about rate law expressions, which are a mathematical equation that relates the concentration of the reactants to the rate of the reaction. It's determined from experimental data. You are not going to be looking at the coefficients of the equation. The coefficients of the equation won't help you. Other things you're going to need to know is the molarity of the solution. Molarity is a way to express how concentrated a solution is. The units are in moles per liter, which might look more familiar to you if we show it as a fraction like that. Or sometimes you're going to see this unit written as moles times liters to the -1 power, the inverse of liters. Sometimes you'll see it written like that. To keep it on one line, it's easier to type that way. The reaction order is the exponent that a reactant's concentration is raised to. It helps you describe the magnitude of the effect of changing that substance's concentration on the rate of the reaction. So the exponent is what we call the reaction order. That's one of the things that you'll be discovering today is the exponent, the reaction order from the data. The overall reaction order is when you take all the exponents and you add them together. That are the exponents in the rate law expression that you're going to derive. The rate constant is represented by the symbol K. A reaction rate constant is, well, it's a constant for a specific reaction, but it is dependent on the temperature. We're not going to be really messing with the temperature that much, but just know that if you change the temperature, that's going to change the value of the constant. The rate constant can be given or it can be determined experimentally. Rate law expressions are based on the following generic formula for the chemical equation, right? This is based on the A plus B turning into C, and it will have this form right here. The rate is equal to the rate constant times, brackets right here are referring to the concentration, the molarity. So if you have reactant A, the concentration of reactant A raised to the power of N times the concentration of reactant B raised to the nth power. I'm going to scroll this down so we can see all this. Those exponents refer to the reaction order of reactant A, what effect it has on the overall reaction rate, and as is M for reactant B. We're not going to include product C in the rate law expression because the rate of reaction is only dependent on how much of the reactants you have to make the reaction happen. The reaction rate's not really dependent on the amount of product. Okay, well, if you turn the page to the next page in this handout, you're going to see, not what you see here, but there's the second page in your handout is sort of a tutorial that represents everything that we're going to go through in these various problems. So that is there for your reference. I'm going to go ahead and work through the problems and invite you to read those directions at the end of this because they might make more sense once you've been through these problems. All right, we are going to have a reaction. Doesn't really matter what the reaction is. We're going to have this generic reaction A plus B mixed together to form compound C. All right, so although that really doesn't matter, but let's just say that that represents the equation. There's a reaction that's not well understood. Fortunately, the following rate information was experimentally determined as shown below. So we have 3 trials of the same experiment, but a couple of things were modified each time we ran the experiment. So the initial concentration of reactant A is here. It's expressed in moles per liter, that's just the unit. We have the initial concentration of reactant B, and we have the rate of that reaction in moles per liter per second. Okay, so that unit can be written as moles times liters to the -1 times seconds to the -1. All right, now what we see here, we're being told to determine the rate expression for this reaction and then to determine the rate constant and then to determine the overall order for the reaction. Okay, so always the simplest way to begin is to start writing the rate expression, because it's pretty generic to begin with, right? There's going to be some rate is going to be equal to the rate constant times the concentration of A times the concentration of B. Okay, so that's where we start. The question is, what are we going to put for the exponents here and here? And so that has to be determined by looking at these various trials, right? Now, when I go up to the trials, what I want to do is in reactant A, we want to find two trials where the concentration of A is constant. Okay, so I have trial 1 and trial 3 where A is constant. What do we see here in terms of the concentration of B? Right, what's happening with the concentration of B? Well, if we look from trial 1, 0.05, to trial 3, 0.10, right? So if we go from trial 1 to trial 3, we see that we have doubled B. Okay, so we've taken B and we've increased its concentration twofold, right? So now what we want to see is, while A is constant and we double the concentration of B, what effect is that going to have on the rate from trial 1 to trial 3? Okay, so here's how we do that. If we see that the rate is doubled, we are going to start with, and I'm going to do this down below here. Okay, if we see that B is doubled, so I'm going to start with the number 2 because that's a doubling. Okay, what has happened? What do we have to do? What exponent do we have to put here? I'm going to say n, to equal an increase in the rate. How much is this increasing? From 4.0 times 10 to the negative 3 up to 1.6. If you were to do this little mathematical equation, times 10 to the negative 2, take the bigger number, divide it by the smaller number, you're going to see that this is an increase of 4 times. All right, so the rate in trial 3 is 4 times bigger than the rate in trial 1. So what that means is, when you double B, what effect does that have on the overall rate? Well, I think you can see here that that n has to be a doubling. Okay, that has to be or a squaring. All right, so what we're doing here is we will then take that exponent, right? So that has to be 2 in order to make 2 to the second has to be equal to 4. So that means the exponent on B, because we changed B, anytime you double B, you're going to square it to give you the rate increase. Okay, so that's how we know the reaction order for reactant B. Let's do the same thing for reactant A. So to look at the effect of A on the rate, we have to find two trials where B has stayed the same. Okay, so where B has stayed the same, that would be trials 1 and trials 2, right? So B is the same here and here. And let's take a look here. From trial 1 to trial 2, we see that that's a doubling of A. So let's go do our little scratch work. If we double A, what's the effect? What power do we have to raise that to get the corresponding increase in the reaction rate? Okay, so what we see here is to go from the rate from reaction 1 to reaction 2, that is also a doubling, right? So if taking the concentration of A and doubling it has an effect of increasing the reaction rate by a factor of 2, then that means that this exponent has to be equal to 1, right? So we say that the reactant A is first order, okay, because it's not going to have an exponential effect on it, right? So what you have just done is you have written the rate law expression for this reaction. That's it. Okay, if we could actually answer part C right away, the overall reaction, the overall order of the reaction is going to be 1 plus 2. You add those two exponents together, right? So overall, this is third order. Okay, so that part is really easy to do as soon as you've written the rate expression. To figure out the rate constant for this expression, what you do is you rearrange the rate law expression for k, because we're trying to find what the value of that is. So k is going to be equal to the rate divided by the concentration of A to the first power times the concentration of B squared. Okay, so that's what we would do to rearrange that equation. Now to figure out the value of k, we just have to pick any one of the three trials. It's not going to matter which one we pick. I'm going to choose trial 1 just because it's the first one in line, and I'm going to substitute in the rate and the initial concentration of A and the initial concentration of B. So if we do that, k is going to be equal to 4.0 times 10 to the negative 3. The unit on that is moles per liters per second. And then we are going to divide that by the concentration of A, 0.050 moles per liter. That's to the first power. Of course, we don't have to write that. Times 0.050 moles per liter. Okay. So what will happen in terms of units, units definitely get a little goofy here. This mole will cancel with that mole. This liter will cancel with that liter, but that's all that's going to cancel. Okay, so but of course I forgot that we need to square that because of that reaction order. All right, so what is this going to do? If I rewrite this, I'm going to get, I'll choose the green pen, if I 4.0 times 10 to the negative 3, right? This is just going to be 1 over seconds in the numerator, and down below, if I multiply those numbers together, 0.050 times 0.050 times 0.050, I get 0.000125. And what am I left with? I am left with moles squared over liters squared. And so what happens when you finally reduce this all down, you're going to get the value of 32. Try it in your calculator. And what will happen is the units, as they divide through, you end up getting liters squared over moles squared times seconds. That right there is the value of your rate constant for that particular reaction. Okay. Rate constant units vary from reaction to reaction depending on what the order of your reaction was. All right, I'm going to continue the problems on a separate video because I have a 15-minute limit on my recordings. So carry on with the next video.